Hey, so I'm going to talk about the most important integral you might learn in this course, the Gaussian integral. You could walk away forgetting everything about double integrals, Stokes' theorem. You could just have never learned them. But if you had learned the Gaussian integral, then you will have picked up something useful from this course because this thing shows up everywhere. So the integral I'm talking about is the integral from minus infinity to infinity of e to the minus x squared dx. This is actually a 1D integral. It's not a double integral. And this thing is called the Gaussian function. And this thing is it's basically everywhere. It shows up in probability because it's the normal distribution. And so, you may have heard of things like the central limit theorem and the law of large numbers. Well, these things come from studying the properties of the Gaussian, and they need this integral, which is the square root of pi. How e and the square root of pi are related is pretty spectacular, but that's not really the point. It also shows up in quantum mechanics. Because it's related to the Hermite polynomials, but really what this is it's the wave function for the harmonic oscillator. Right, I mean, like in classical mechanics, you have a spring, right? Well, you can treat this using quantum mechanics methods like you would just for the hydrogen atom. And so then when you do that, the solutions look like the Gaussian functions. They don't look like sines and cosines anymore. Okay, and it also just shows up in mathematics. If you ever study pure mathematics, this thing, it helps you do all kinds of nice stuff. Like it helps you with the Fourier transform. Like you don't have to know what this means, but it turns out that if you Fourier transform this thing, you basically get itself back, which is a pretty awesome thing. So now with all this buildup, let me actually talk about how to evaluate this integral because it's actually pretty cool. And don't worry, we haven't talked about what infinite limits mean. And the reality is it doesn't matter because there's no, with a nice function like the Gaussian, which looks like this, then there's no problems with infinities really, because this thing is so small that you could well approximate the integral by just truncating it to some finite interval like minus 1,000 to 1,000, because e to the minus 1,000 squared, that's really, really small, so it doesn't really contribute to the integral, right? So that's, I mean, I'm just saying, don't get freaked out by infinity. Just treat it as the same thing. Okay, so how do you evaluate the Gaussian integral? Well, it's this really crazy trick, but it's worth knowing just because the integral is so important. And the reason I'm bringing it up is because it uses polar coordinates. This is why they did not teach you this thing in single variable calculus. You actually need to do a double integral. And so the reason is that if you add an extra term, x squared plus y squared, and now you integrate this thing over all space, you can do it using polar coordinates. So if you switch to polar, this becomes, well, let's just draw the region. I mean, that's a square, right? But really it's the entire space. So your radius, it could be 0, but it could also be anything, right? Because it's all of R2. So your radius goes from 0 to infinity. So if this is your R integral, that goes from 0 to infinity. And your angle can also be anything. There's no angle preference. So for your theta integral, you integrate from 0 to 2 pi. You can see now where our original pi is going to arise from, right? It's going to come from the angle. So hopefully there's going to be a factor of 2 that goes away. And in fact, we can see why almost immediately. First of all, we have e to the minus r squared. That's what this thing is, right? That's why I put that y squared there, because I wanted to get the r squared out of it. And then finally, when we change the area, we get r dr d theta. Remember, now it has dimensions of meters squared, so it's a real area. So now you can see where the 2 is, right? Because here's the r squared and here's the r, so there's going to be a factor of 1/2 after you do a u sub. So this is actually separable. It's a product, right? Because the theta integral decouples. It's the integral from 0 to 2 pi of 1 d theta times the integral from 0 to infinity of e to the minus r squared r dr. And this thing is, if you do a u sub of r squared equal to u, you get 0 to infinity 1/2 e to the minus u du. And that's pretty easy. That gives you 1/2 e to the minus u from 0 to infinity. And see why I told you the infinity doesn't matter? Because obviously e to the minus u looks like this, so the infinity term is 0. And the 0 term is just 1. So this ends up just being 1/2, because the 0 gives you a negative sign. So on the other hand, the theta integral is just 2 pi. So there's that 1/2 that we wanted. We end up getting that this double integral over all space, this ends up giving you pi. Well, we're pretty close, right? Because we wanted square root of pi. So now it's a double integral. That's where the 2 will come in. That's what we'll get, because the 1/2 will give you that square root. So how do we get that? It's because we use this awesome property of the exponential where it factors out into products. And products are one of the only things we can do with double integrals. And just so happens that's exactly what we want. So if we separate this out, we get 2 Gaussian integrals. Both of the same limits, remember, because it's all over R2. Yeah? So that means, well, we could just call this x again. There is no x. There is no x here. This is a dummy variable. So I'm going to replace all the y's with x's. So that's just this thing squared, right? So if I call this integral Gaussian, so then it says that g squared is pi. So g equals square root of pi, and that is exactly the Gaussian integral. Let me just, if you haven't seen the dummy variable thing, let me just briefly mention why that is. If you just think of it as a Riemann sum, you can see that y is just, it's kind of arbitrary, because what this is it's -1 squared delta y, or let's say like 0.1, plus -1 plus 0.1 squared times 0.1, and so on. So there is no x. These are just numbers. Yeah, you should have seen that in single variable calculus, but I'm just mentioning here just because it does allow you to get that square. Okay, so this shows you how to get the Gaussian integral. There's actually several other ways to do it, each of which is harder than the last. So this is kind of a neat method that we can see already in multivariable calculus. Okay, thanks for watching.